Welcome to the Huberman Lab podcast, where we discuss science and science-based tools for everyday life. My name is Andrew Huberman, and I'm a professor of neurobiology and ophthalmology at Stanford School of Medicine. This podcast is separate from my teaching and research roles at Stanford. It is, however, part of my desire and effort to bring you zero-cost-to-consumer information about science and science-related tools. In keeping with that theme, I'd like to thank the sponsors of today's podcast. Our first sponsor is Headspace. Headspace is a meditation app that makes meditation easy. I've been meditating on and off now for about 30 years, although I confess more off than on. And that's because I think, for a lot of people, sticking to a meditation practice can be pretty challenging. I started using Headspace a few years ago, and I found that it's really allowed me to stick to a meditation practice on a regular basis. I meditate anywhere from 5 to 7 times a week. The app includes meditations that are all backed by scientific peer-reviewed studies, and it makes it really easy to start and complete the meditations. I started using these meditations while I was flying a few years back. On JetBlue flights, they started offering Headspace meditations, so that's where I initially started, and then I moved over to the app, and I really enjoy it, and I derive great benefit from it. If you'd like to try Headspace, you can go to headspace.com/special offer. And if you do that, you'll get all the meditations that Headspace offers for free for 1 month. That's headspace.com/special offer. You get all the meditations for free, which is the best offer that Headspace has available right now. So if you're interested in it, check it out. The second sponsor of today's podcast is Athletic Greens. Athletic Greens is an all-in-one vitamin mineral probiotic drink. I started using Athletic Greens in 2012, and I've been using it continuously ever since. I started using Athletic Greens because I found it rather dizzying to know which vitamins and minerals to take, and Athletic Greens allows me to get the full base of all the necessary vitamins and minerals in one easy-to-consume drink. It also turns out that the drink tastes quite good. I mix mine with some lemon juice and some water. I'll drink it once or twice a day. The probiotics in Athletic Greens are also important to me because there are a lot of data now supporting the fact that the gut microbiome is important for the gut-brain axis, for various aspects of cognitive function, immune function, metabolic function. There's just a huge number of things that having a healthy gut microbiome has been shown to be important for. So by taking Athletic Greens, I have that base covered as well. If you'd like to try Athletic Greens, you can go to athleticgreens.com/Huberman. And if you do that, they'll give you a year's supply of liquid vitamin D3K2. There are also a lot of data now showing that vitamin D3 is very important for a number of different biological functions. In addition, they'll give you 5 free travel packs with your order. It can be difficult to mix up powders while on the road, when in a car or, in a hotel or on a plane, etc. The travel packs make everything really clean and easy. So you'll get the year supply of vitamin D3K2 plus the 5 free travel packs if you go to athleticgreens.com/Huberman. The third sponsor of today's podcast is Made4. Made4 is a behavioral science company that makes learning positive habits and growth mindset easy. I've been involved with Made4 since the beginning as the lead of their scientific advisory. Other members of the scientific advisory include, for instance, the head of the chronobiology unit at the National Institutes of Mental Health, as well as psychiatrists from Harvard Medical School and elsewhere, all of whom are serious about science and science-related tools for developing positive habits and growth mindset. The program is a 10-month program during which each month you engage in a specific activity designed to encourage and cultivate positive habits and growth mindset. As well, we hold a monthly Zoom call during which we discuss the program, people's progress, and answer any questions they have directly. If you'd like to try Made4, you can go to getmade4.com, and if you put Huberman in at checkout, you'll get 20% off the program. That's getmade4.com, put Huberman in at checkout, and get 20% off the program. Today, we're going to talk about how to change your nervous system for the better. As you recall, your nervous system includes your brain and your spinal cord, but also all the connections that your brain and spinal cord make with the organs of your body, and all the connections that the organs of your body make with your brain and spinal cord. Now, this thing that we call the nervous system is responsible for everything we know, all our behavior, all our emotions, everything we feel about ourselves and the outside world, everything we think and believe. It's really at the center of our entire experience of life and who we are. Fortunately, in humans, unlike in other species, we can change our nervous system by taking some very specific and deliberate actions. And today we're really going to focus on the actions, the motor commands, and the aspects of movement and balance that allow us to change our nervous system. It turns out that movement and balance actually provide windows or portals into our ability to change our nervous system the way we want, even if those changes are not about learning new movements or learning how to balance. And soon you'll understand why. So today we're going to talk a lot about the basic science of neuroplasticity. I promise to not use excessive nomenclature. There'll be a little bit, but I'll try and make it as clear as possible. And we're also going to talk a lot about protocols and tools that the scientific literature points to and supports for changing our nervous system. Again, not just for sake of learning new motor movements or how to balance better, but for how to feel differently about particular experiences, both past, present, and future, as well as how to learn faster. We're not going to discuss hacks, a word I loathe. We're not going to discuss gimmicks. We're going to discuss mechanism and scientific data and the tools that those mechanisms and scientific data point to so that you can tailor your practices around learning to your specific needs and goals. So let's begin by just examining the big picture question, which is, does the brain control behavior? And my hope is that everyone is immediately thinking yes. The brain and nervous system, we really should say, because the brain is just one component of the nervous system, controls our behavior. How does it do that? Well, there are a couple different levels that it does that. First of all, if we're talking about movement, behavior generally means movement. If we're talking about movement, we have two categories of neurons that are very important to think about in the context of neuroplasticity. First of all, we have what are called lower motor neurons. These are motor neurons that live in our spinal cord. If for the aficionados out there, for those of you that might be head to medical school or just want to learn more about the anatomy, they live in the ventral horn of the spinal cord, but that doesn't matter. If you don't want to know that, just know that you have these things called lower motor neurons. These are neurons that are in the spinal cord, but they extend a wire that we call an axon out into the peripheral nervous system, into the body, and those neurons connect with muscle. They send electrical potentials out there that allow our muscles to twitch and to contract. As a little point of fact, actually, we don't have muscle memory. There's no such thing as muscle memory. Muscles are dumb. They don't know anything. They don't have a history. They don't have a memory. They don't know anything. It is the neurons that control those muscles and their firing patterns in which all the information for motor patterns are stored. So your ability to walk is not muscle memory, it's neural memory. Now the lower motor neurons, while smarter than the muscle, so to speak, are not the most brilliant of the motor neurons. They are generally involved in doing what they are told. And they are told what to do from two sources. We have circuits in our brainstem, so this would be kind of around your neck, deep in the brain, that are called central pattern generators. These are sometimes called CPGs. Central pattern generators are what allow us to generate repetitive patterns of movement. So inhaling and exhaling subconsciously is controlled by a central pattern generator. That just means a collection of neurons. If you really want to know, they're called the Prebot-Singer neurons, discovered by Jack Feldman and colleagues at UCLA. These neurons in the brainstem send information down the phrenic nerve and control the diaphragm, so it goes inhale, exhale, and you don't have to think about that. You could think about it, and you could change the durations of inhales and exhales and change that up, but the motor neurons that control that are just responding to what the brain is telling it to do. The other central pattern generators include things like walking, the right limb, left limb pattern that we normally associate with walking was learned during childhood, and these central pattern generators, sometimes called CPGs, tell our lower motor neurons, fire, now you fire. So they are literally saying right, left. They are the marching orders from the brainstem to the lower motor neurons. So these lower motor neurons do what they are told. They are obedient little soldiers, and they do what they are told, and their job is to make the muscles contract at specific times. Okay, that's all simple. But then there are the upper motor neurons. the upper motor neurons actually reside in our motor cortex, way up on top of the brain. And they are involved in sending signals for deliberate action. Okay, so they send signals to the lower motor neurons, which are the effectors, the ones that actually control the muscles, but the upper motor neurons are the ones that send very specific signals. For instance, the signals that would allow you to make a cup of coffee in the morning or to deliberately engage in any kind of behavior. Now, you can probably make a cup of coffee in the morning without having to think about it too much. It's almost reflexive for you now, which means that a lot of the information about how to perform that particular movement has been passed off to circuitry that's now more or less in the brainstem and below the motor cortex. Now, why am I giving you all this detail? Well, if you want to change motor patterns, you have to know where in the circuitry changes are possible, and you ought to know where the changes are most likely to occur. You also need to know how do you signal to the brain and nervous system that a change is necessary. So let's just pause there, return to the initial question that we started with, which is, does the brain control behavior? And the answer is yes, and now you know how. It's upper motor neurons, lower motor neurons. You've got these things called central pattern generators and some connection with the muscle. So there you go. You just got basically what was the equivalent of the introduction to a college lecture on motor control in the nervous system. But the point today is all about plasticity. How can that be leveraged in order to open up this magical thing that we call plasticity in order to access changes to our emotional experience or to our belief system or to our ability to remember and use specific kinds of information for, say, math or language, etc. Well, what I'm not going to tell you is that you need to go running or you need to go biking or that simply going through motor patterns is going to open up plasticity, because I hate to tell you this, but as beneficial as exercise is, it does not open plasticity unless you do certain things. And I will tell you exactly what those certain things are today. To be clear, I think exercise is wonderful and healthy, can improve cardiovascular function, maintain strength, bone density, all that good stuff. But just working out or doing your exercise of various kinds will not change your nervous system. It will maintain it, and it can certainly improve other health metrics, but it is not going to open up the window for plasticity. The question we need to ask is, can behavior change the brain? We already agreed that the brain can change behavior, but can behavior change the brain? And the answer is yes, provided that behavior is different enough in specific ways from the behaviors that you already know how to perform. Let me repeat that. Can behavior change the brain? And the answer is yes, provided that behavior is different enough from the sorts of behaviors that you already know how to perform. And I should have added the word well, because you can't obviously perform a behavior that you don't know how to perform because you don't know how to do it yet. But there's a key element to accessing neuroplasticity that, frankly, I don't see out there in the general discussion about neuroplasticity. In the general discussion about neuroplasticity and about learning, I hear all these gimmicks about using different ways to remember lots of people's names and arranging things into their first letters and mnemonics and all this kind of stuff, which frankly to me feels really gimmicky. And I think that if you look at super learners, they tend to be people that have a process of, say, extreme memory. But people who have extreme memory generally, the literature shows us, are pretty poor at other things. So I don't think most of us are interested in walking around knowing how to remember everything. In fact, there are some interesting studies looking at humans who over-remember, and they suffer tremendously because they remember all sorts of things, like the number at the top of the receipt at the bodega that they bought a Coca-Cola 10 years ago. This is useless information for most people. They don't do well in life, really. So the goal isn't to remember everything. The goal is to be selective about your brain changes. And when we talk about brain changes, I want to highlight adaptive changes. There's a whole category of things that we're going to discuss when we talk about traumatic brain injury and dementia, a topic for a future episode, about all the things that happen when you have damage to your nervous system or you're missing neurons. But today, I really want to talk about something that I think is very near and dear to many of your hearts, which is, what are the behaviors that you can engage in to access neuroplasticity so that then you can apply that plasticity to the specific things that you want to learn or unlearn. This is very important because I don't want people to get the impression that we're really talking about learning a bunch of motor movements. You may be an athlete, you might not be an athlete. You might want to learn how to dance, you might not. You might want to learn how to dance and get better at remembering and learning languages, for instance, or at unlearning some difficult emotional experience, meaning you want to remove the emotional load from a particular memory of an experience. What we're talking about today is using behavior as a gate to enter states of mind and body that allow you to access plasticity. So let's talk about the different kinds of plasticity that are available to us, because those will point directly towards the type of protocols that we should engage in to change ourselves for the better, the so-called adaptive plasticity. There is something called representational plasticity. Representational plasticity is just your internal representation of the outside world. So you have a map of auditory space, believe it or not, meaning you have neurons that respond when something over on my right happens, like I'm snapping my fingers over to my right. Can't snap as well on my left, which is the whole thing into itself. Weak over there on the left side. But when I do that, there are different neurons respond to those. We have a map of visual space. Certain neurons are seeing things in certain portions of visual space and not others. We have a map of motor space, meaning when we move our limbs in particular directions, we know where those limbs are, because even if we can't see them, we have what's called proprioceptive feedback. So we have knowledge about where our limbs are. In fact, people that lack certain neurons that for proprioceptive feedback, they are very poor at controlling their motor behavior. They get injured a lot. It's actually a terrible situation. So we've got all these representations inside, and we have maps of our motor commands. We know that, for instance, if I want to reach out and grab the pen in front of me, that I need to generate a certain amount of force, so I rarely overshoot. I rarely miss the pen, okay? So our maps of the motor world and our maps of the sensory world are merged. The way to create plasticity is to create mismatches or errors in how we perform things. And this, I think, is an amazing and important feature of neuroplasticity that is highly underappreciated. The way to create plasticity is to send signals to the brain that something is wrong, something is different, and something isn't being achieved. And I think this will completely reframe the way that most people think about plasticity. Most of us think about plasticity as, okay, we're going to get into this optimal learning state or flow, and then suddenly we're going to be able to do all the things that we wish that we could do. Well, I hate to break it to you, but flow is an expression of what we already know how to do. It is not a state for learning. And I'm willing to go to bat with any of the flowanistas out there that want to challenge me on that one. Flow is an expression of nervous system capabilities that are already embedded in us. Errors and making errors out of sync with what we would like to do is how our nervous system is cued through very distinct biological mechanisms that something isn't going right, and therefore certain neurochemicals are deployed that signal the neural circuits that they have to change. So let's talk about the experiments that support what I just said, because I'm about to tell you that making errors over and over and over again is the route to shaping your nervous system so that it performs better and better and better. And I'm not going to tell you that the last rep of a set where you hit failure in the gym is anything like neuroplasticity. You hear that too, that, it's pushing to that point of a cliff where you just can't function anymore. That's the signal. That's not the signal. That's a distinct neuromuscular phenomenon that bears zero resemblance to what it takes to get neuroplasticity. So let's talk about errors and making errors and why and how that triggers the release of chemicals that then allow us to not just learn the thing that we're doing in the motor sense, play the piano, dance, etc., but it also creates an environment, a milieu within the brain that allows us to then go learn how to couple or uncouple a particular emotion to an experience, or better language learning, or better mathematical learning. It's a really fundamental aspect of how we're built, and when you look at it, it's actually very straightforward. It's a series of logical steps that once you learn how to open those hatches, it becomes very straightforward to deploy. Last episode, we discussed some of the basic principles of neuroplasticity. If you didn't hear that episode, no problem. I'll just review it quickly, which is that It's a falsehood that everything that we do and experience changes our brain. The brain changes when certain neurochemicals, namely acetylcholine, epinephrine, and dopamine, are released in ways and in the specific times that allow for neural circuits to be marked for change, and then the change occurs later during sleep. I'll review that later, but basically, you need a certain cocktail of chemicals released in the brain in order for a particular behavior to reshape the way that our brain works. So the question really is, what allows those neurochemicals to be released? And last episode, it talked all about focus. If you haven't seen or heard that episode, you might want to check it out, about some specific tools and practices that can allow you to build up your capacity for focus and release certain chemicals in that cocktail. But today we're going to talk about the other chemicals in the cocktail, in particular dopamine. And we're really going to center our discussion around this issue of making errors and why making errors is actually the signal that tells the brain, okay, it's time to change, or more generally, it's time to pay attention to things so that you change. And I really want to distinguish this point really clearly, which is that I'm going to talk today a lot about motor and vestibular, meaning balance programs, but not just for learning motor commands and balance, not just for learning new motor skills and balance, but also for setting a stage or a kind of condition in your brain where you can go learn other things as well. So let's talk about some classic experiments that really nail down what's most important in this discussion about plasticity. As I mentioned last episode, and I'll just tell you right now again, the brain is incredibly plastic from about birth until about age 25. Passive experience will shape the brain just because of the way that the chemicals that are sloshing around in there and the way that the neurons are arranged and all sorts of things. The brain's job is to customize itself in response to its experience. And then somewhere about 25, it's not like the day after your 26th birthday plasticity closes, there's a kind of tapering off of plasticity, and you need different mechanisms to engage plasticity as an adult. We're mostly going to be talking about adult plasticity today, but I got a lot of questions about, well, what about if I'm younger than 25? Well, first of all, that's great. I wish I could. I wish I had a time machine, but I don't, because as I've said before, the stinger is when you're young, your brain is very plastic, but you have less control over your experience. When you're older, generally, you have more control over your experience, but your brain is less plastic. So if you're already asking the question as a 20-year-old or a 15-year-old, what can I do now that's really going to enhance my brain? I guess the simple question would would be an aside, which would be get the broadest education you can possible. That means math, chemistry, physics, literature, music, learn how to play an instrument. I'm saying that because I wish I had, etc. Get a broad training in a number of things and find the thing that really captures your passion and excitement, and then put a ton of additional effort there. That's what I recommend, including emotional development. Maybe a topic for a future episode. But if you are an adult or if you are a young person, knowing how to tap into these plasticity mechanisms is very powerful. You need these chemicals deployed in the nervous system in order to mark whatever nerve cells happen to be firing in the time afterward for change. And people are obsessed with asking, what supplements, what drugs, what conditions, what machines will allow for that. But there's a natural set of conditions that allow for that. When we came into this world, we learned to take our different maps of experience, our motor maps, our auditory maps, our visual maps, and to link them. We align those maps. The simplest example is the one I gave before. If I hear something off to my right, like a click like that, it could come from my finger snapping, or it could come from something generated by somebody else or something else to my right. I look to my right. If I hear it on the left, I look to my left. If I hear it right in front of me, I keep looking right in front of me. And if I hear it behind me, I turn around. And that's because our maps of visual space and our maps of auditory space and our maps of motor space are aligned to one another in perfect register. It's an incredible feature of our nervous system. It takes place in a structure called the superior colliculus, although you don't need to know that name. Superior colliculus has layers, literally stacks of neurons like in a sandwich, where the 0 point right in front of me, or maybe 10 or 15 degrees off to my right or 10 or 15 degrees off to my left, are aligned so that the auditory neurons, the ones that care about sounds at 15 degrees to my right sit directly below the neurons that look at 15 degrees to my right in my visual system. And when I reach over to this direction, there's a signal that's sent down through those layers that says 15 degrees off to the right is the direction to look, it's the direction to listen, and it's the direction to move if I need to move. So there's an alignment. And this is really powerful, and this is what allows us to move through space and function in our lives in a really fluid way. It's set up during development, but there have been some important experiments that have revealed that these maps are plastic, meaning they can shift. They're subject to neuroplasticity, and there are specific rules that allow us to shift them. So here's the key experiment. The key experiment was done by a colleague of mine who's now retired, but whose work is absolutely fundamental in the field of neuroplasticity, Eric Knudsen. The Knudsen lab and many of the Knudsen lab scientific offspring showed that if one is to wear prism glasses that shift the visual field, that eventually there'll be a shift in the representation of the auditory and motor maps too. Now, what they initially did is they looked at young subjects, and what they did is they moved the visual world by making them wear prism glasses, so that, for instance, if my pen is out in front of me at 5 degrees off center, so just a little bit off center. If you're listening to this would be like just a little bit to my right. But in these prism glasses, I actually see that pen way over far on my right. So it's actually here, but I see it over there because I'm wearing prisms on my eyes. What happens is, in the first day or so, you ask people, or you ask animal subjects or whatever, to reach for this object, and they reach to the wrong place because they're seeing it where it isn't. This gets especially complicated when you start including sounds, when you have a thing off to your right making a sound, but the thing is actually right here. So you're hearing the sound at one location and you're seeing the object at another location because you're wearing these prisms. So your image of the world is totally distorted. Or in experiments done by other groups, they wear glasses, subjects wore glasses that completely invert the visual world so that everything is upside down, which is an extreme example of these representational maps being flipped or shifted. But what you find is that in young individuals, within a day or two, they start adjusting their motor behavior in exactly the right way so that they always reach to the correct location. So they hear a sound at one location, they see the object that ought to make that sound at a different location, and they somehow are able to adjust their motor behavior to reach to the correct location. It's incredible. It's absolutely incredible. Or in the case of the people who look at the world upside down, they somehow are able to navigate this upside down world, even though we're completely used to our feet being on the floor and not on the ceiling, and people not walking at us by hanging off the ceiling like bats. Amazing. And what it tells us is that these maps that are aligned to one another can move and shift and rotate and even flip themselves. And it happens best in young individuals. If you do this in older individuals, in most cases, it takes a very long time for the maps to shift, and in some cases, they never shift. So this is a very experimental scenario, but it's an important one to understand because it really tamps down the fact that we have the capacity to create dramatic shifts in our representation of the outside world. So how can we get plasticity as adults that mimics the plasticity that we get when we are juveniles? Well, the Knudsen lab and other labs have looked at this, and it's really interesting. First of all, we have to ask, what is the signal for plasticity? Is it just having prism glasses on? No, because they did that experiment and ruled that out. Is it just the fact that the visual thing is appears to be far over to my right when in fact it's right in front of me? No. The signal that generates the plasticity is the making of errors. It's the reaches and failures that signal to the nervous system that this is not working, and therefore the shifts start to take place. And this is so fundamentally important because I think most people think, oh, well, practice is going to be, I have to access beginner's mind, which is a great concept, actually. It's about approaching things expecting to make errors, which is great. I think I am a believer in beginner's mind. But people understandably get frustrated, like they're trying to learn a piece on the piano and they don't know how, they can't do it, or they're trying to write a piece of code, or they're trying to access some sort of motor behavior and they can't do it. And the frustration